in previous class, we saw how to store and go through different data in pandas library. So, in this this class, we'll get started with machine learning. So, there are basically three types of machine learning models that we can say. One thing is, first one would be supervised learning, second one would be unsupervised, and third one would be reinforcement learning. So in supervised learning, we know the output that we want, and we are trying to build a model that can give us the output. In unsupervised learning, we do not have any output that we want, but we want to do some kind of analysis on data. And in reinforcement learning, we have an environment in which our learning system can uh, exhibit some behavior, and depending upon the outcome, it might be rewarded or be penalized. So you can say that reinforcement learning roughly falls between supervised and unsupervised learning. Uh, Reinforcement learning mainly currently is being worked in robotics and mostly in robotics itself, right? uh, uh, Rest of the things that we might see, like image classification, or like what kind of disease classification we have, this will be some supervised learning. And some things like recommender systems, like uh, Netflix recommendation system or YouTube recommendation system, can be roughly called unsupervised uh, task. So since we do not know what kind of prompt a user might click on, unless until he clicks on it, we do not know the data or the outcome of the uh, task we get. So this could be unsupervised learning. We'll go through the different examples, and you'll get a bit more clearer differentiation. Hopefully, you're going through this hand accordingly. Let's see, suppose here we have classification, predicting discrete levels. So our data has two columns, say feature 1 and feature 2. We have plotted different features here, and we know the labels of each. Say is like number of students who have attended classes, amount of time they spent, and this would be this blue or red is like did they pass or fail. So uh, depending upon different tasks, you can say that people, these kind of people have passed the exam and these they have failed. This is the data that we have. So we can draw a line between them. You can see this. So we can draw a line between these two clusters, and get a general idea about the whole data. Say, suppose a new student comes, and they have two different features. If we'll plot them, and if the point lies below this line, there might be in a failure. If the point lies above this line, it might be a pass student. This is like the prediction that we have. Now, how do we fit this line? This is the task that the machine does for us. You might have remembered basic line fitting that goes through different points in your like first year or second year classes while you're doing your experiments. These are nothing but fitting the lines onto the given. So there are roughly four kind of things available for us. Classification saying this belongs to this class, not the rest of the other classes. Regression says like classification would be like is this a dog, a cat, a bird, some discrete point in the whole spectrum. Regression might be a continuous value, how much percentage a student might achieve. It might be 50%, 51%, 70%, 90%. So predicting a continuous value is a regression problem. Predicting a discrete value is a classification problem. Discrete value in the sense the total number of outputs are a discrete set. Say suppose we have in a college we have two types of systems, and is would provide the percentage after the exam has been done. So it might be 60%, 70%, 80%, 81, 81.5. And another same college might have one more thing called grading: A grade, B grade, C grade, A minus, B minus. So A minus, B minus, C minus, these kind of grading can be we need to predict. We need to predict these kind of labels. It would be a classification problem. If we want to predict the percentage, that percentage can go from anywhere. Say it might be 80, 80.5, 90, 90 point, something like that, or a continuous value. So it does not mean continuous value like a real number, but compared to the total number of points, it's continuous. Where uh, people might be 80%, 81%, 81.5%, and 82%. This can also be kind of considered as a continuous prediction. Even though there are only like three values that we can find between 80 and 81, might be 80, 80.5, and 81. On the whole, when you see it goes from 0 to 100, and roughly there are 200 outputs that we have. But for the same data, we might have say 5 grades, 5 to 7 grades. The whole students can fall in. So this kind of thing is called classification, and continuous prediction is called regression. And these two are kind of supervised learning, that we know what grade or what percentage that a student can get. Suppose we do not have such kind of data, but we have previously passed or failed data. So then we can plot them or try to cluster them. Here you can see there are different features. All the these all kind of people are at this point. All people are at this point. So there are A, B, C, D grades, but we do not know that they were graded in this way. So what we do is, suppose this is our data that is available for us. So there are people with this kind of features, and we did not know that these people got A, these people got B, these people got C, and these people got D. So then what we do is we try to cluster them depending upon the similarity between the neighbors. So suppose these two people are very close together. So we can say they are in the same class, but this fellow and this fellow are far away. So we might consider them as different group, different classes. And this is kind of gets blurry when you see these two dots, right? These two dots are a bit similar, sorry, a bit closer, but we have to assign this in real this person got a B, and this person got a C. So we do not have exact boundaries what we have to do, but we try to cluster the most similar people together. It might be some cases, might the extreme cases might we might predict falsely, but most of the people that lie inside this will get a correct prediction. So there is considering these two groups, there might be some similarity here. This group is a bit totally isolated when compared to the distribution of the whole. So these people have a bit more. They do not have that much variance when compared to the rest of the people. So suppose we have. One second. So this is one class. This is the other. So let's consider these people. They have the variance is between these points, and along this axis, the variance is like this. When compared to the rest of the people, the variance of these people along this feature is a bit similar, just shifted a bit, but along this feature, the variance is very broad, like right. So we can consider these as a single group, and we can consider all of them into another group just by looking at it. And now this is just a visual thing that we just see and try to do some clustering, and then afterwards we'll try to build some algorithms that can give us these clusters. So now let's say we are done with this part. We have clustered them into one group. Now coming to these rest of three groups. See here, these two groups are very close together when compared to this. So what we do is we select a center point. We select one point and we try to find the distances between all the other points. So points for each point, we'll add all the distances and we'll keep it for each point. And then having all these values together, we can say we'll put a threshold, and within this threshold, if this point is similar to all the other points, we'll label them a single label. Similarly, when compared to this distance, this is this is greater than the threshold we set. So this will not be assigned the value blue, but something else. So it generally depends upon the whole variance of our data. We can actually say, suppose we group these two together. Somehow we group to there was one data point here that that was such that the distance from them and distance from this was same, and we kind of made all this data together. And then when we have this point as our anchor, then this all will also have the same distance, right? So this might also be fall under the same group. This part you can see that all these can be one group and this can be one group. That might be one of the reasons that all these people can be globbed together. This just depends upon the different parameters that we use, the cutoffs that we put, so that we can achieve our result. So these parameters that we try to change, so the distance from a center to all the points, that would be one parameter. So if we set that parameter exactly, precisely, then we'll get the accurate value. But we do not know the value what to put. Say suppose if we put it very small, only these 2 points will be in this class. Rest of the all the points will be mislabeled. Or if we put the value to be very large, it will be most of the different points will be misclassified. So there is a this can be a parameter for our model. These kind of parameters are called hyperparameters. So mainly the part of the data scientist is to try to find the optimum hyperparameters for a given model so that the prediction is quite accurate. Yeah, so now this clustering is a bit unsupervised algorithm. One more unsupervised algorithm is that we have is dimensionality reduction. So dimensionality reduction is nothing but we have suppose 10 features. So here we have only two features, right? So X feature and Y feature. So our X1 and Y1. These are only two features that we have. Suppose you have a many large number of features. Say suppose we have data of different houses in some area. It might be the area of the house, length, width, closeness to an airport, access to a road, uh, uh, view to a lake or view to a beach. There are different features that a lot of different features that are available for us for a single data point. Then what we do is we try to only pick the relevant features so that the maximum amount of information can be expressed with minimum number of features. So suppose we have length, width, and area. So once we have length and width, we do not have to consider the area because the area is just the product of length and width, right? Suppose let's suppose all the houses are in are a rectangle or a square. So that the area is kind of redundant feature, or else you can put the area and remove length and width from the data. So either we need to have mainly most of the time the amount of square footing the a house occupies will be proportional to the cost it might be valued at, right? So either we have length and width or we have area. So one more thing you have to keep in mind is when you're trying to remove the data, you have to be very careful. Suppose say we are trying to find this data on some India in Hyderabad, let's say. So buildings that have access to the main road along the length and access to the some buildings might not have access to the main road. So some most of the buildings that have access to main road might have some kind of shopping available for them. So it's like the ground floor of that building might be different shops are there, so it might be taxed heavily and things like that. So by just putting the area in our data, we are missing out the crucial information. So a building that has shops in the bottom and some residence in the above might be a bit more costlier when compared to the same thing that do not have any shops at the bottom. So you need to understand your data, how the data has been extracted and how it's being presented. So data analysis, data scientists, these are all things that go in hand to each other. At one point of time, you put on a data analyst hat, and at one point of time, you put on a data scientist hat. You need to switch from one way of thinking to another, depending on the task at hand. So dimensionality reduction, as you understand, is removing some kind of data and preferably keeping the most relevant data. One of the examples that you might have come across is the eigenvalue and eigenvectors. So you might have did this, right? Given a matrix, find the eigenvalues and eigenvectors. You might have math 1 or math 2. So these eigenvalues represent the length of represents the important of the feature, and the eigenvector gives the direction in our multidimensional space. It gives us the direction in which most of the points might lie. So by going through the largest to the lowest eigenvalues, we can say that the highest eigenvalue has the most important information along its axis, and the least eigenvector has the minimum information along this axis. So we can remove all the irrelevant features, and we just keep the first two eigenvectors. Let's say suppose we have 1,000 columns in our data, and we just get two columns that are relevant for us. So these two columns are not specifically the two columns that you can pick along the data frame. It's just two direction in our multidimensional space that gives us the information. Yeah. Well, so now we have a new library called scikit-learn, Scientific Kit-Learn. So this is the one of the important libraries that deals with machine learning. Most of the algorithms that Andrew NG teaches are available in this library. You can just utilize them outright of the library to get some hands-on information. So suppose previously we saw this iris data set, right? Different flowers having sepal length and petal length, sepal width and petal width, and the species which they belong to. So we'll get this data. Most of the libraries have this iris data set in, because it's very small data set, and it's a good example for starters. Seaborn is another library similar to Matplotlib, but it's a bit more visually pleasing. It's like I would say it's like iOS, and Matplotlib is like Android. A bit more visually pleasing when compared to Matplotlib. Uh, so here we can plot with a single line called pair plot. This will plot the whole data set along with different axes. So we have here we have sepal and sepal width, petal length, petal width, right? So we'll have each this petal length will be plotted across petal width, petal length, and petal. Yeah. So see, petal width is plotted sepal along on the axis of sepal length, sepal width, petal length, petal width. So just by giving this one example, one uh, method, we can directly plot the whole thing. In Matplotlib, we have to go through each and every data point, do subplots and the whole thing. Seaborn does the whole thing in the backend and just gives us the representation that we need. So you can see there are different clusters available for us, and while plotting sepal length along sepal length, we get a kind of distribution that is available. So there are say most of the blue are setosa. So most of the setosa lengths are between these points, and this is the distribution of the different lengths available. So most of the values are around 4 4 centimeters, and here in the green one, being zoom. So this thing. So the green is a bit more distributed, so it's a bit more variant, and the maximum is, like most of the petals have sepal length around this value. We're just taking only, yeah, here we do iris is where we have our data. Here we see iris is where our data has been loaded, and we are trying to put the x values, all the x values into x underscore iris. This contains all our features, and y iris is the labels that we have. So labels will be 0, 1, or 2, things like that. In total, there are 150. See, here we see there are 150 data entry points and 4 features available. And for each flower of 150, there is a corresponding label attached. So here, see, this contains, this is the number of samples that we have. This has the features. That each column is a different feature. And finally, we have a target label. So if we have this target label, the task will be supervised. If we do not have this target vector thing, then it would be an unsupervised task. So, yeah. Now let's see some different APIs available, things available for us in scikit-learn. So now let's plot this random points. So this is some you did some experiments and you found out this is the data distribution, and you need to get the line best fit line along all these points. What we do, we try to fit a linear model. So what does a linear model do? It creates a line that is y equal to mx plus c. So m and c are the variables here, right? So depending upon different values available in the graph, it will try to plot. So here we have, so m and c are the parameters. So since by changing one each and every m value and each and every c value, we might fit the data perfectly or not. So we call them as hyperparameters. So on we fit that just by we'll create a. Sorry, we need to import the linear regression model from scikit-learn, sklearn. Dot linear models. There are different linear models. We import linear regression. So, so here you can see all the different things available for us. So don't get overwhelmed by all the things that are available here. There are a lot of many things available, but depending on your task, you'll understand what to do. So we are trying to fit a linear model, right? So here we come into linear models. There are different linear models available for us. So there is logistic regression, uh, there is a perceptron, ridge classifier, SGD, different algorithms that try to fit onto a linear class. So if there are regression and linear classification models. So we created a model that has fit into intercept as true and fit intercept, and one is M and one is C. So now we are putting all the values that we created, all these values into a data frame. So or a numpy array. So there are 50 points that we plotted, and we are trying to fit those values. We give in the x values and the y values here. X is our value, the output on the y-axis. And just by putting model dot fit and giving the data here, we can train our model. So it is very easy because there are only 50 points available. So it's a bit fast. As you increase the number of data points, it will take a bit more time to get the output. By doing model dot coefficient and model dot intercept, we will get the m value and c value. Coefficient is the m value, intercept where the line intercepts the x-axis. So now we have this thing done. We can see how it fits our data. So here was these dots were our data points, and this is the line that we have plotted. This is the best fit line considering the linear model. Suppose our these points are non-linear. Say suppose they are in a parabolic way. Fitting a line might not be the precise thing that we should do, but yeah, so if we want to fit a quadratic model, and we can import the quadratic model and try to fit it there. So let's do this for our iris classification. So now okay, there was some update 1 month ago. So this might not work exactly. So one more thing that is very useful in Google Colab, it directly gives us a Stack Overflow link that we can search. So it has been the thing is like previously sklearn dot cross validation import test train split. This was the way that we imported this test train split, and this was deprecated, and it was changed to this model selection. So here we can just copy this thing, paste it back there. So using Google Colab, you saw right, just a single click of button got us to the Stack Overflow page, and we found out what is the error about, and we can fix it. Now we are trying to, here we are using some Gaussian NP. Let's see what is this in the API. So here you will come in this search it here. So Gaussian MBA naive Bayes, and Gaussian is a kind of distribution that we extracted. So this you'll go through in the Andrew MG lectures. What is naive Bayes, and also we'll go through in the in-depth lectures also. Don't worry about it. It's just to show how things are done. So now we are importing the Gaussian naive Bayes model. We are instantiating the model class. So this is a class of naive Bayes. We are instantiating a model, and we have this model dot fit. This will do the training with the X train data and Y train data, and then we give out the prediction on the exit test. So, and you can see, let's see the accuracy. So it has classified, it has given us 97.97.5 accuracy. So similarly, we can get to the principal component analysis or dimensionality reduction. So dimensional principal component analysis is nothing but getting the most the longest direction in which the eigenvector is largest. So the eigenvalue is largest in which we'll get the direction of that eigen value, and we'll just remove the rest of the data. Similarly, as previously from scikit-learn decomposition. So previously we had some linear model. First we had for this we are linear. Here for this we have naive Bayes. Next from this scikit-learn we have decomposition. We have imported PCA. We'll do the same thing. We need to get the top two components, and we are trying to fit the data, and we have the accurate model type transfer. Transforming the RL data is like removing the unnecessary data. So by we previously we had 4 points, right? Sepal and sepal with petal and then petal. So all those points have been compressed into two dimensions. PCA1 is the main principal and the secondary principal. Now we can do some kind of classification. Here. Imagine if you have some thousand features. So say suppose this number of features here is like 1,000 columns long, then we are trying to just compress into just two columns that will contain most of the information. Now we are trying to cluster to the unsupervised. We are trying to cluster them. I think we can pause it for here for today's class. If you have any doubts, you can ask me. There is a bit of construction that they started. It's very short, but it's here. Thank you guys for it.